All right, number 21 wants us to find the volume of a region here that's bounded by x is equal to the square root of y and x equals 0, just limited on this range right here. That's the right word, from 1 to 4 for our y values, and this whole thing is being revolved about the y-axis. So let's see what we're dealing with right here, guys. X is equal to the square root of y. That's unusual. You don't see that too often right there. If you squared both sides, it would be y equals x squared, which is just a normal upwards opening parabola. But because it's just the positive square root of y, not the negative square root of y, we're just dealing with the right half of this graph, everybody. So that's all we've got right there. X equals 0, of course, is our y-axis. So I'm drawing that border right there. And they just want us to deal with this thing between y equals 1, which is right here, and y equals 4 right over here. So they've given us really 4 different borders here, guys, and that is going to create this two-dimensional region for us here. So that's what we're starting with here. And now we're spinning that region, it says, about the y-axis. So I'll draw the 180-degree reflection of that, which is going to be roughly something like this. Probably not perfect, but good enough. There we go. And this thing is going to look, let's see, something like this up on top. And on the bottom, you'll see that edge, but this will be a hidden line right over there. Okay, so 2 quick, again, not decisions, but determinations we have to make. Is this a dx or a dy problem? We are going here, everybody, around the y-axis right here. That automatically then makes this a dy problem. The second distinction we have to make is, are our cross sections here going to be discs or washers? And I think in the notes I used the phrase circles rather than discs. But as you can see, guys, there is no gap here between this yellow region and the axis of revolution. No space at all. So our cross sections, no matter where it is that you cut them out, are going to be solid circles. So we're using the discs or circles method, not washers. All right, so that's what we have. And our radius is going to go right here, looking something like that. All right, guys, so what do we need to do? The area of a disk or a circle, obviously, is pi times your radius squared, and the radius then, running horizontally, will be right curve minus left curve here. The right curve is this one right here. X is equal to the square root of y, so r is going to be the square root of y minus the left curve right over here, which is x equals 0. So our radius is just the square root of y. That tells me then that area, written as a function of y, is going to be pi times your radius, root y, squared. And this is convenient. The square and the square root cancel, and we just end up with area is equal to pi times whatever your y coordinate is. Okay, so then volume is going to be the definite integral, we said taken with respect to y, of this area formula right here, pi times y. And I'll bring the pi out in front and just leave y for the only part of the integrand. That worked out okay. Limits of integration, lowest and highest values of y. This thing begins right here when y is 1 and ends right up here when y is 4. So those are the limits of integration here. So what does that do for us, guys? We've got a pi, and then the antiderivative of y is going to be a 1/2 y squared, evaluated from 1 to 4. I'll put the pi and the 1/2 together and make that a pi over 2. And then in brackets, here we go. 4 squared is going to be 16 minus 1 squared, which is going to be 1. And we're going to end up then with 15 pi over 2 cubic units for the volume of that solid. There's really nothing we can do to simplify that. So there's our answer for number 21.